Welcome back to another deep dive. Today, we're taking a look under the hood of something really foundational for understanding our energy future. We've got this detailed source on energy system definition inputs from a pretty powerful model called EnergyPLAN. So our mission really is to ask, what does it actually take to model, transitioning an entire country's energy grid? How do experts even begin to define and measure something so huge? What are the building blocks? What kind of granular data do you need to make sense of it all? We're going to try and uncover the crucial inputs, the things that dictate how these models work, and maybe what that tells us about the real-world dance of energy demand and supply.
Yeah, and in a world that's striving for sustainable energy, understanding these models is just, well, it's absolutely key. They let us move beyond guesswork, right?
Yeah.
Beyond just abstract ideas. They help build these comprehensive, data-driven pictures of what energy futures could look like. So we'll be looking at the four main areas users define in EnergyPLAN: demand, supply, balancing and storage, and costs.
Okay, so when we picture an energy system, yeah, we often think power plants, supply. But you're saying the real starting point, maybe the most complex bit, is understanding demand. How does EnergyPLAN even start mapping out what a society actually needs energy-wise?
You're spot on. Demand is foundational. I mean, for any serious energy system analysis, technical or economic, getting that demand and supply data right is indispensable. The core demand categories in EnergyPLAN, they range from, electricity, heating, cooling, industry, transport, and even desalination, which surprises some people.
That is quite a list. Okay, let's start with electricity demand then. It's not just about the total annual gigawatt hours, is it? How does it capture those minute-by-minute changes, the peaks and troughs? What does knowing that let you do?
That's a great question. No, it's definitely not just the annual total. The model captures what it calls flexible electricity demands. So this means you can model how demand shifts, through a day, a week, even over 4 weeks, and you also define the maximum capacity for those flexible loads. The real insight, is that understanding these shifts allows for much smarter grid management, especially with renewables coming in. It even lets you subtract things like electric heating or cooling demand from the total electricity demand to get a clearer picture of the actual grid load, shows how things interact.
Right, so you can see how switching to electric heat pumps, for example, impacts the grid specifically. Okay, so that level of detail on electricity, it leads us straight into heating, another huge chunk. How does it handle the complexity of how a whole society stays warm?
Yeah, heating is fascinatingly detailed in this model. It wants really nuanced inputs. Everything from individual boilers you specify, fuel type, like coal, oil, gas, biomass, and their thermal efficiency, all the way to combined heat and power, CHP units, and heat pumps. And for those, it tracks both electrical and thermal efficiencies, plus capacity limits. It gets really granular. You can even define CHP capacity as a sort of share of maximum heat demand. And that's crucial because it helps figure out where, peak demand might still need those old school boilers to kick in.
And I saw it includes solar thermal too, like on individual houses and in district heating systems. That really shows it can integrate renewables right down at that level, doesn't it? Even accounting for heat losses in the pipes for district heating.
Absolutely. It aims for that completeness. Then moving to transport, beyond the usual suspects, jet fuel, diesel, petrol, natural gas, LPG, the model really emphasizes detailed inputs for battery electric vehicles, BEVs, and also vehicle-to-grid, V2G, cars. Which raises a pretty interesting question for you, I think. How tricky is it to model something as dynamic as V2G? Cars feeding power back. The model needs inputs like maximum share of cars driving during peak demand hour, and the capacity of the grid-to-battery connection. It's trying to capture behavior and infrastructure limits.
That sounds incredibly complex, trying to predict driver behavior and grid capacity at the same time. Wow, and then you mentioned desalination. That was surprising. So you're saying the model simulates fresh water demand, water storage, and even uses pumped hydro storage for the leftover brine, and figures out the desalination plant size needed hour by hour.
Exactly. It integrates critical resource management like water right into the energy system analysis. It's not just electrons and heat.
Okay. Mine's slightly blown on the demand side detail. So once we know what energy we need, how do we tell the model where it's coming from? What does the supply side look like? Is it just as detailed?
Oh, absolutely. The breadth of supply inputs is, it's vast. You've got your heat and electricity production units, CHP, boilers, standard power plants.
Yeah.
Then there's central power production. That's things like big condensing power plants, nuclear, geothermal, hydro. After that, you define variable renewable electricity sources, plus heat-only sources, different fuel distribution networks, waste-to-energy plants, and then a whole complex array of liquid and gas fuels, including biofuels and synthetic fuels. Each needs its own data.
Right. Let's dive into that central power production bit. Nuclear and geothermal, they're usually seen as base load, right? Just
Sure.
running flat out. But you mentioned a correction factor. It lets you adjust their output even if the capacity is fixed. What's the practical use of that kind of dial?
That correction factor is actually super useful for scenario planning. It's like a fine-tuning knob, exactly. Well, yeah, nuclear and geothermal provide baseload. This lets you model situations where maybe a plant runs slightly below max output, perhaps due to maintenance or regulations, or maybe even slightly more if it's optimized somehow. It lets you simulate those real-world operational nuances without fundamentally changing the installed capacity number.
Okay, that makes sense. For realism. And linking that to hydropower, its flexibility is modeled really carefully too, isn't it?
Yes, hydro's flexibility is key. It's modeled meticulously. You input the annual water supply, the reservoir storage capacity, the generator efficiency, and then the model iteratively adjusts the hydro production based on how much water is actually in storage. It makes sure the system balances out over the year so the storage level ends where it started. It's quite a sophisticated way to capture hydro's ability to ramp up and down.
Got it. Okay, now, the big one for the energy transition, variable renewables, wind, solar, etc. The model lets you define capacities for up to 7 types, like onshore wind, offshore, PV, wave, even concentrated solar power. What was the biggest sort of aha moment for you in how it models these variable sources, especially their actual energy output?
Yeah. The aha moment for me was definitely the correction factor for renewables as well, FGAR as they call it. It lets you adjust the production, the energy generated, without physically changing the installed capacity. So, for example, the source notes that with a 1,000 milliW of wind capacity, applying a correction factor could make the annual output jump from roughly 2 TWh a year to over 4 TW a year. Same idea for solar PV 500 milligo could go from zero point 0.5 TWh to over 1 TWh. It really highlights that a renewable asset's contribution isn't just its nameplate capacity. It's hugely dependent on, grid integration, curtailment policies, maybe even tech upgrades within that capacity. Shows massive potential just in optimizing what we have.
That is a powerful insight. Yeah. How we manage and optimize existing assets is just as vital as building new ones.
Okay, what about waste? You mentioned waste to energy. How does EnergyPLAN view waste in the system?
Waste is treated quite cleverly, actually, almost like a special kind of biomass energy. The key thing is it cannot be stored but has to be burned regularly. But it's not just about burning it for heat and electricity. The model allows it to be potentially converted into, say, biofuels for transport or CHP, or even into various non-energy products that might have economic value. It gives this sort of holistic view of waste. It's a resource with multiple potential pathways, not just something to incinerate.
It's interesting. A more circular economy approach integrated in. And then the sheer diversity of liquid and gas fuels you mentioned. Biofuels, biodiesel, biopetrol, biojet fuel, even noting food byproducts. Biogases from different sources, hydrogen from electrolyzers, electrofuels like synthetic gas or liquids. That level of detail for fuels that are still, emerging in many cases must be hard to populate with solid data. You absolutely hit on a key challenge there. The level of detail, like modeling the specific efficiency of biomass to biodiesel, or the electricity needed for CO2 capture in electrofuel production, it is mind-boggling. The challenge isn't just the volume of data points, it's ensuring accuracy and consistency. Especially for those newer emerging fuels, the data might be less mature or less certain. So you'd likely need to run sensitivity analyses, testing different assumptions to see how much those inputs really matter to the final outcome.
Right, testing the what-ifs. Okay, so we've got demand mapped out, supply sources defined. What happens when the system actually has to run, hour by hour, day by day? How does it stay stable, especially with all those variable renewables? And the big question, who pays for all this infrastructure and energy?
Okay, yeah, the balancing and storage section tackles that stability question head on. It addresses the critical real-world challenge of grid stabilization. Particularly in systems with lots of renewables, keeping the grid stable is paramount. So the model can be set to require a certain percentage. The example used is often 30% of total electricity to come from specific grid stabilizing units. Think large power plants, flexible CHP. But then it also looks at the opposite problem, critical excess electricity production, or CE, too much power. And it offers, believe it or not, 9 different strategies to deal with that excess. Things like curtailing renewables, or maybe ramping up electric heating or electrolyzers. It lets the user prioritize how the system sheds load in a controlled way.
9 strategies for too much power.
Yeah, okay.
And storage is obviously key to balancing, too. It supports pumped hydro, batteries, hydrogen, even rock bed storage. What's that? High-temperature heat storage. Why model all these storage types in such detail?
Rock bed storage is indeed high-temperature thermal storage, yeah. Modeling storage with this granularity is vital, precisely because storage is the linchpin for managing renewables variability. By getting into the nitty-gritty, like the specific fuel ratio for compressed air energy storage CAES systems, or how that rock bed storage can effectively replace fossil fuel consumption for heat, the model really emphasizes storage isn't just one thing. It's an ecosystem of solutions, each with different characteristics, helping manage fluctuations, boost resilience, and just enable much higher levels of renewables.
Makes sense. It's not just a big battery. Okay, on to the money, the economics. How does EnergyPLAN handle costs?
Right, for a proper market economic simulation or a, feasibility study, the cost data is absolutely crucial. It includes the obvious things: investment costs for each power plant or boiler type, their expected lifetime, fixed operation and maintenance O&M. But it gets incredibly detailed on fuel costs. It breaks them down into world market prices, plus handling costs, plus different taxes. And these can vary depending on who's using the fuel. Like the tax might be different for a household compared to a central power plant. This allows for a really quite realistic economic assessment. It also figures out variable O&M costs and calculates marginal production costs based on fuel prices and taxes.
Wow, okay, different tax levels included.
Yeah.
And it even models interacting with an external electricity market, factoring in price elasticity, how much demand changes with price. That shows real economic depth, doesn't it?
It really does. It simulates how import-export prices might fluctuate between a defined maximum and minimum based on how much you trade. That market interaction is essential. No energy system operates in total isolation. And finally, but critically, there's emissions. The model lets you define specific emission factors for things like SO2, particulate matter, PM2.5, AOx, methane, N2O for every single technology. It's a fairly simple calculation in the end, just multiplying fuel consumption by the emission factor. But it's powerful because it directly links the technical operation of the system to its environmental impact, which is obviously vital for policy and sustainability goals.
What an absolutely incredible deep dive that was. We've really seen how EnergyPLAN takes this incredibly detailed, almost bottom-up approach, from those flexible electricity demands and heating system complexities to that huge array of supply options, including those optimized renewables and electrofuels, and then layering on the crucial balancing act, storage in all its forms, and those really meticulous cost and emission factors.
Yeah, I think understanding the inputs at this granular level, it just reveals the enormous complexity involved in actually planning and transitioning our energy systems. It really forces you to move beyond abstract goals into thinking about the concrete data points, the relationships, the trade-offs that drive real-world outcomes. It informs much better decisions, hopefully.
So knowing how meticulously these models are designed, how much detail they can capture, what new questions does that raise for you listening right now about the data that we maybe should be collecting? Or perhaps the policy decisions that need laser focus to truly shape our energy future effectively? Something to think about. Thank you so much for joining us on this deep dive. Until next time, keep exploring the absolutely fascinating world of energy systems.